Hello, Advanced Algebra students, and welcome back to another video lesson as we continue to explore imaginary numbers and complex numbers. Today we're going to look at operations with complex numbers. So if you've got your air guitar ready, let's rock on and get going. Now, complex numbers, imaginary numbers are very similar in a sense, you'll see in a moment, but as I talked about a little bit the other day, some applications are that, engineers, people that build or look at building things, use I to study the stresses on beams or the resonance of which, that stress might impact a beam. Complex numbers can help us study the flow of fluid around certain objects, like water around a pipe or other things. And it's really big here in electric circuits or transmitting radio waves. So, if it weren't for we might not be able to talk on cell phones or even listen to the radio. There's a little bit of applications to this in math and art too, but really it's nothing more than expanding a little bit of algebra. So complex numbers are when we have the real parts combined with the imaginary parts. That together makes it a complex number, typically of the form A plus BI, where A represents the real part and the BI represents the imaginary part. So as we solved in some of yesterday's problems, we actually were working with complex numbers, not just imaginary. And because it's at the top of the hierarchy here, all numbers that we have can be written as a complex number. All right, we were working a lot and talked about imaginary, but even all of our numbers that we've traditionally worked with since like kindergarten and preschool are actually technically called complex, and they could be written in this form, A plus BI. So let's take a look at what that might look like. I'm working out of your packet, page 7, and here's 3 of them. Identify the real and the imaginary parts. So in letter A, the real part is obviously the number 4, because that doesn't have an I. And the imaginary part is going to be the negative 10I. So that one's pretty straightforward. Here's my A and here's my BI. But when we get to letter B, it's a little bit trickier, right? What's our real part? What's the real part to this one? Well, it would be 0, because there is no real part. And then our imaginary here is going to be negative I, or negative 1I if you prefer to put the 1. Letter C, what's the real part? Well, the real part is 12, because that does not have the I value on it. So what's the imaginary part here? Well, in this case, we can't just put 0, because 0 is not an imaginary number. So we have to put 0I. We need to make sure that we include that letter I anytime we talk about the imaginary. And so that's why any number we're working with can technically be written as a complex number. 12 plus 0I is a complex form. Now, you may be wondering, what's the big deal with all of this? Well, there's a big idea that comes out of all of this, right? If we have 5 plus 2x plus 3 plus 4x, and we've simplified that in the past by combining like terms, we get 8 plus 6x. What do you think that means if I'm using the complex number system? 5 plus 2i plus 3 plus 4i. Well, it's very similar in that we treat that I value almost as if it's its own variable. We can only add imaginary parts together, and we can only add real parts together. And that's the big idea in this complex numbers lesson, right? The properties of basic operation are assumed and hold true with complex numbers. If I can add real numbers together, I add real numbers together. If I can add like terms together, I add like terms together. If I can multiply, and so on and so forth. And that's where we're going to take this lesson today. So here are a couple of examples for adding and subtracting with complex numbers. Think of this as like terms. But the like terms in this part are adding and subtracting the real parts together, and then adding and subtracting the imaginary parts together. Negative 5 plus this 8 would give me 3 for the real parts. 6 plus negative 9i would give me negative 3i for the imaginary parts. 3 minus 3i. If we look at the second one, 7, now we're subtracting, so 7 minus 8 becomes negative 1. And then 6i minus negative becomes plus 5i. So 6i plus 5i is plus 11i. So we can always add the real parts together, and we can always add the imaginary parts together. That's one of those basic things we've worked on since regular algebra class. Same thing with multiplying. All right, we can multiply and still continue to distribute. We can multiply a lot of things together. Just don't forget that we could use FOIL or the distributive property here, or even the box method. So I'm going to draw some lines. Distributing 5 times 4, which becomes 20, plus 5 times 3i becomes 15i, plus 6i times 4 is 24i, plus 6i times 3i is 18i squared. So now we're going to focus next on just combining like terms. These two have like terms. They're both just i's. So 20 plus 39i plus 18i squared. However, what we've learned the last couple of days is that this I squared part can really be substituted with negative 1. I squared is negative 1, so 18 times negative 1 would give me negative 18 out here, or 20, plus 39i minus 18, and now I've got a real number and a real number that can get combined together. 20 take away 18 is 2, plus that 39i. 2 plus 39i. And so we're really using that distribute box FOIL method to help us break this down into A plus BI. And the proper way, whenever we have our answers, is to start with the real number, or A, or if you have other variables, and then BI comes a second. Why don't you pause the video and try this second one? So again, I'm just going to distribute 3 times 3. That gives me 9. Plus 3 times the negative 5i is negative 15i. This 5i times 3 is positive 15i. And then 5i times negative 5i is negative 25i squared. All right, I see an I squared again. So that I'm going to replace with negative 1. And negative 25 times negative 1 becomes adding 25 out here on the end. Negative 15i plus 15i, that gives me 0i. And we have 9 out front, or 9 plus 25, which becomes 34. 34. So again, a couple pieces eliminate there. So I'm treating I almost as if it's an x, as if its own variable, until I get to the end, where if I notice I have an I squared, I can substitute that negative 1 in there. Why don't you try these two? See what you get here in these two. Write our answers in the form A plus BI. I'm going to add my real numbers. Negative 4 and 8 becomes 4, plus 5i plus negative 9i is negative 4i. I'm going to stop right there because I cannot add real and imaginary together. In our second one, we've got a subtraction sign, so 7 minus that 8. 7 minus 8 becomes negative 1. 3i minus negative becomes plus. So 3 plus 5 is plus 8i. Negative 1 plus 8i. Next set. See if you can simplify these two. All right, the first one, we've only got 2 multiplications to do, 2 distributives. 7i times 9 is going to be 63i minus, because I've got a subtraction sign, 7i times 6i minus 42i squared. But don't forget that this I squared really becomes negative 1, or 63i plus 42. Negative 42 times negative 1. And then we've got to make sure we put the real number first. 42 plus 63i. And the second one, we've got 4 multiplications to do. 5 times 6, that's my 30. 5 times negative 2i is negative 10i. 7i times 6 is a positive 42i. 7i times negative 2i is negative 14i squared. So hopefully you're picking up on the pattern. I squared changes to negative 1. And negative 14 times negative 1 becomes positive 14 on the end. 30 out front. Negative 10i plus 42i gives me 32i, and then I can combine the real numbers that I still have left to get 44 plus 32i. So that's a lot of the operations that we can do with these complex numbers, very similar to solving and simplifying algebra. Last question for today is more of a challenge. All right. Is 3 plus I a solution to the quadratic x squared minus 6x plus 10 equals 0? Explain your answer. Basically, this means to show your work. Now, we could definitely go to the quadratic formula, since we know that a is 1, we know b is negative 6, and we know that c is 10. So we could plug that in and see if we come up with this as an answer somehow. However, I'm going to take and see, I'm going to plug this in for all of the x values in here. 3 plus I quantity squared minus 6 times 3 plus I plus 10. And whatever I get over here, I want it to equal 0. Does that equal 0? You've got to be careful with 3 plus I quantity squared. 3 plus I times 3 plus I. We'll forget to do that for multiplications if we don't write it out twice. 3 times 3 is 9, plus 3 times I is 3i. I times 3 is plus 3i. I times I is I squared. So this chunk gives me 9 plus 6i minus 1, because the I squared changes to minus 1, or we are left with 8 plus 6i. 8 plus 6i from that whole thing. And then let's distribute here. Negative 18 minus 6i plus 10. Well, notice I've got a positive 6i and a subtracting 6i. So those are going to cancel each other out. 8 minus 18 is negative 10. And negative 10 plus 10 is 0. Does that equal the 0 on the other side? It certainly does, which means that is indeed a solution. And so we can plug that in for the x's and use our substitution methods in simplifying. Or you could go into the quadratic formula. and simplify. If you have any questions, please make sure to reach out. Otherwise, until next time, everyone, stay safe